Good morning, dear students. I am Dr. Jyotirmayi from the Department of Chemistry. Today, I would like to discuss about one of the important alkaloid, that is morphine. In the last class, we have discussed about the general methods of structural elucidation, how we separate the alkaloid from the plant material, how we purify the compound, and then finally we have discussed about the general methods of structural elucidation. Today, with reference to the morphine, let us discuss the structure and synthesis of morphine. As we have seen in the last class, a similar picture we can also see here. This morphine is obtained from Papaver somniferum. That is, in Telugu we call it as gasagasalu. So from this plant, except from the seeds, either from the straw or from the leaves, we will get morphine. This is a very important alkaloid. Along with morphine, we will also find codeine and thebaine. These two alkaloids are also present along with morphine. So this is the actual structure of morphine. Here you can see one benzene ring, adjacent to that another 6-membered ring, another 6-membered ring. And here you can see the heterocyclic ring where the nitrogen is attached to ethyl group. And here the ether linkage is present where the oxygen is present between two carbon atoms. So altogether there are 5 rings, A, B, C, D and E. So now we shall study the structure of morphine. As we have discussed about the general methods in which we study the structural elucidation, first of all, we must find out the molecular formula. I have already mentioned in the previous class that the molecular formula can be obtained by combustion analysis. By burning the compound by combustion, we will get the percentage of carbon, hydrogen, oxygen and nitrogen. From percentage composition, we will get the empirical formula. From the empirical formula, we will get the molecular formula. So, the molecular formula of morphine was found to be C17H19O3N. 17 carbons are there, means it will have 3 or 4 or more than that rings, and there are 3 oxygens and 1 nitrogen. So that is about the molecular formula. So after finding out the molecular formula, we have to know the nature of the functional groups. Here we can see that there are 3 nitrogens and 1 oxygen. So we have to find out the nature of the functional groups in which the oxygen and nitrogen are present. So here we have only 1 nitrogen, that's why first we shall see the nature of the nitrogen. In the general methods we have seen that we have to find out the nature of the nitrogen, whether it is in the primary, secondary or tertiary state. As morphine adds 1 molecule of methyl iodide, that is, we take the alkaloid and add methyl iodide. It was observed that it adds 1 molecule of methyl iodide to form the quaternary salt, which confirms that it is having a tertiary nitrogen atom. So, with the help of Herzig-Meyer method, we have found out that the nitrogen is carrying the methyl group. So, finally, what can we say about the nitrogen? The nitrogen is in the tertiary state and the nitrogen is carrying a methyl group. Then we have to find out the nature of the oxygens. Here we have 3 oxygen atoms. So we have to find out the nature of the oxygens one after the other. First, second and third oxygens. So first we discuss about the nature of the oxygens. As we have discussed in the general methods, first we will test for the hydroxy group. Similarly, here also morphine on acetylation, that is, either we can treat it with acetic anhydride or acetyl chloride. or we can treat it with benzoyl chloride. So on acetylation or benzylation, it gives diacetyl or dibenzoyl derivative. So two acetyl groups are formed or two benzoyl groups are formed means there are two hydroxy groups. So monoacetyl derivative indicates the presence of one hydroxy group, whereas diacetyl derivative indicates the presence of two hydroxy groups. So we have three oxygens. Among the three oxygens, we have two oxygens in the form of hydroxy groups. As we have discussed in the general methods, after finding out the nature of the oxygen in the form of hydroxy, we have to confirm whether it is in the form of alcohol or it is in the form of phenol. For that, we test it with neutral ferric chloride. So with the ferric chloride, morphine yields color. It gives a color reaction, which indicates that one of the hydroxy group is phenolic in nature. So out of three oxygens, two are hydroxy. Out of two hydroxy, one is alcoholic and the other one is phenolic in nature. Then we have to find out the nature of the third oxygen. So in order to know the nature of the third oxygen, it is allowed to undergo degradations, as we have seen in the general methods. So in degradation also, there is no degradation that is taking place, which indicates that the oxygen is inert. The oxygen is not taking part in any of the reactions, which indicates that it is not free. It is in the ether linkage. That means the oxygen is clamped by two adjacent carbon atoms. So it might be in the ether linkage. So we have one nitrogen. Nitrogen is in the tertiary state and the nitrogen is carrying the methyl group. And we have three oxygens. Out of three oxygens, two are giving hydroxy reactions. And out of the two, one is alcoholic, the other one is phenolic. Coming to the third oxygen, it is found to be inert, not taking part in the reactions, which indicates that it is in the form of ether linkage. Then we have to find out whether there is any unsaturation or whether there is any ethylenic bond. So when codeine is nothing but a methylated morphine. The codeine is reduced catalytically in the presence of palladium. It takes up one molecule of hydrogen. That means it adds one molecule of hydrogen, which is possible only when there is a double bond. So as codeine adds one molecule of hydrogen, indicates and confirms the presence of a ethylenic double bond in morphine. So morphine contains one ethylenic double bond. Then we have to test for the benzene nucleus. So morphine on bromination yields monobromo derivative. So the formation of the monobromo derivative indicates the presence of the benzene nucleus. So morphine on treating with bromine gives monobromo derivative, which confirms the presence of one aromatic ring in benzene. So we have found out the nature of the nitrogen, we have found out the nature of the oxygens, we have to find out the nature of the carbon skeleton. And we have 17 carbon atoms. So it might be having more than 3 rings. So if 3 rings are there, nitrogen must be present in some other ring. So it is not very easy to know the carbon skeleton. So we have to allow the alkaloid to undergo number of reactions. For that, we allow the degradation with zinc dust. When morphine is distilled with zinc dust, it yields phenanthrene. So phenanthrene means here you can see 3 benzene rings attached to one another. So on zinc dust distillation, as it forms phenanthrene, it indicates the presence of the phenanthrene nucleus. So this is also confirmed by number of reactions. As we know, codeine is methoxy. or methyl morphine. On treating with methyl iodide, it yields codeine methiodide. This on further treatment with alkali gives codimethine. This alpha codimethine on alkali treatment gives beta codimethine. Either of these isomers on treating with methyl iodide followed by alkali yields methyl morphinol, which is treated with hydrogen bromide gives morphinol, which on reduction with sodium alcohol gives morphol, which confirms the presence of the phenanthrene nucleus. So here, as we have to know the nature of the carbon skeleton, we are allowing it to undergo zinc dust distillation. So zinc dust distillation gives a phenanthrene as a product which confirms the presence of phenanthrene nucleus. Further, we can confirm by treating codeine with methyl iodide. We'll get codeine methiodide, which on treating with alkali gives codimethine. So this codimethine on further reactions gives methyl morphinol, and this methyl morphinol finally gives methyl morphol. So this methyl morphol on further reduction gives morphol. Morphol contains phenanthrene nucleus, which confirms the presence of phenanthrene nucleus in morphine. So here we can see 3, 4, 5 trihydroxyphenanthrene. So we start from here, number 1, first carbon, second carbon, third carbon, fourth carbon, fifth carbon. So there are 3 hydroxy groups. So 3, 4, 5 trihydroxyphenanthrene is formed from morphinol. So what is morphinol? Morphinol is the phenanthrene nucleus with hydroxy and ether linkage. This on treating with potassium hydroxide, it gives trihydroxyphenanthrene. On the other hand, morphinol on reduction with sodium alcohol gives morphol, which finally confirms the presence of the phenanthrene nucleus. So this phenanthrene nucleus contains altogether 14 carbons. So here we can have 6 carbons, here we have 6, 12, in addition 13 and 14. 14 carbons are there. As we know, morphine contains 7 carbons. So we have found out the carbon skeleton for 14 carbons. We have to find out the nature of the other carbons, how they are present. So we allow it to undergo further reactions. So till now, we have found out that there is one benzenoid ring with phenanthrene nucleus, and in exhaustive methylation and followed by alpha codimethine, it was observed that there is a nitrogen carrying the methyl group and 2 more carbons are attached to the nitrogen on the other side. And it also contains a double bond. The nitrogen is found to be tertiary in nature. Based on these reactions, we can write the following structure for morphine. So this is the phenanthrene nucleus having 1 hydroxy on the aromatic ring and ether linkage and another hydroxy. And the nitrogen is attached to the methyl on one side and 2 carbons on the other side, and there is 1 double bond. So we have to add this part of the molecule to the phenanthrene nucleus, and we have to add the double bond. So then we can finally come to the conclusion of the structure of the morphine. So now, how the nitrogen attached to the carbons are attached to the phenanthrene nucleus. So we have to find out the point of linkage of this group to the phenanthrene nucleus. For this, we allow codeine to undergo oxidation with chromic acid, where some hydroxycodeine along with quinone is formed. The hydroxycodeine on exhaustive methylation yields ketocodimethine, which on heating with acetic anhydride yields methoxy diacetyl So thus, when oxidized, it further gives quinine with the loss of acetoxy group. So we can write down all the sequence of the reactions. We have taken codeine. What is codeine? Codeine is nothing but methyl morphine. This on oxidation gives hydroxycodeine. So this hydroxycodeine on exhaustive methylation gives ketocodimethine. That is, the hydroxy group is oxidized to the keto group. So this ketocodimethine on treating with acetic anhydride followed by acetylysis gives methoxy diacetoxyphenanthrin. This on further oxidation gives methoxy monoacetoxyphenanthraquinone. So from these reactions, we can come to the following conclusions. As there occurs the loss of one acetyl group in the oxidation, methoxy diacetoxyphenanthrin to methoxy monoacetoxyphenanthraquinone, this reveals that one of the acetoxy groups in the former compound must be either present on C9 or at C10. So if you go to the previous slides, we can see that this is the first carbon, second carbon, third carbon, fourth carbon, fifth, sixth, seventh, eighth, ninth, and 10th. So now we are discussing about the point of linkage of the nitrogen attached to the phenanthrin nucleus. So these are the two positions which are free. 9 and 10 are the positions which are free, where the nitrogen can be attached. So the nitrogen can be either on the 9th carbon atom or on the 10th carbon atom. So for this we have to further study. Now since the S-toxic group which is lost in the oxidation is inserted in position by a ketonic group in the acetylysis, it means that the keto group in ketocodimethine and therefore the new hydroxy group in S-toxycodeine must be present at C9 or C10. On the basis of the steric consideration, the attachment at C9 is most probable. So we can finally conclude that the point of linkage of the nitrogen is at C9. So the nitrogen is present at the 9th carbon atom. So starting from here, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The nitrogen is attached to the 9th carbon atom. So based on those reactions, we can write the structure of the morphine. So here we have written codeine. Only thing is in the place of methoxy, we can write OH. Then we'll get the structure of morphine. So this is the phenanthrin nucleus with one benzene ring and one hydroxy on the 3rd carbon, and the ether linkage between the 4th and 5th carbon atoms, and hydroxy at the 6th carbon atom, and the nitrogen is attached to the 9th carbon atom. So if this is the structure of codeine, this on oxidation gives hydroxycodeine. So this hydroxy, that is the carbon at the 10th position, is free. So here we'll get the formation of the hydroxy. This on Hofmann exhaustive methylation, where the ring, heterocyclic ring, will be broken. So we'll get the product. This on further reaction gives ketocodimethine. This on treating with acetic anhydride gives the further products. So when we have seen that the side chain containing nitrogen is always eliminated during the aromatization of the phenanthrin nucleus. But we have already shown that the nitrogen end of the side chain is linked to C9. That nitrogen is attached to the 9th carbon. Therefore, the carbon end of the side chain must be located at angular position, and the possible positions are C13 and C14. So the nitrogen part of the heterocyclic ring is attached to C9. What about the carbon part? So where this carbon is attached to close the ring. So what are the possibilities? If this is the 9th carbon, 10th carbon, 11, 12, 13 and 14. Here there is no possibility. Already all the positions are occupied by the the